well or do domain-specific language extensions work, and how can we find out? That was the question we've asked. More specifically, we've evaluated domain-specific extensions of C for embedded software development by doing an industrial case study. So the case study was the development of a smart meter. It's something you plug into your electrical mains in order to measure voltage, current, compute various values, communicate them back to the utility. And one of the important aspects of this tool or of this device is that precision is critical for certification. So it needs to be fast, the software needs to be fast, and evolvability is critical to be a business success. So the software architecture and the implementation needs to be some degree of flexible. And this thing has been developed with mbeddr, which is a set of domain-specific extensions to C. And as you can see on this following slide, we have all kinds of extensions for state machines, physical units, components, verifications, and integrations with the development process. And these extensions, that is what we've evaluated mostly in the case study. Here is a screenshot. It's not very well visible on this somewhat over bright beamer, but you can see that we use text notations, tables, graphics, all in one IDE. And this is also part of the thing we wanted to evaluate. Do these different notations help? So, setup of the case study. It's an industrial project. This is very good for realism, right? It's a real project with real requirements, real size, real deadlines, real developers. It's not so good for reproducibility because the source code is proprietary. That's also why this is not artifact evaluated. I couldn't hand out the source code. mbeddr itself is open source, but the smart meter implementation is not. So what were the research questions specifically we were asking? First of all, we were asking whether these extensions to C help with dealing with the complexity of implementing such a system and which abstractions are specifically useful, which were missing. We were looking at how is the testability of such an implementation of such a system affected by these extensions. We were hoping, of course, for it to be improved because we have better abstractions so we can test better. Kind of that was something we wanted to look at. Overhead. Abstraction tends to induce overhead. You know, things getting slower or requiring more memory. That's something we were looking at. And then the effort. Does this thing introduce more effort or reduce the effort? Because obviously all these nice things are, if they all, you know, if you get all these benefits, but it's 3 times more effort, then it's probably not viable. What was the data we collected? Well, in terms of complexity, we looked at qualitative impact of mbeddr and the smart meter specific extensions on complexity. For testing, we measured the test coverage, looked at how much smart meter specific code had to be written. In terms of overhead, we compared the size of the binary to the resources of the hardware. We did not have a non-mbeddr implemented smart meter for us to compare. We didn't do it twice. So we had to essentially look at the resources available. And in terms of effort, well, we investigated and looked at the efforts reported by the developers, right? So we just looked at the timesheets, essentially. So here's the hardware architecture of the system. It's a 2-processor thing with 2 MSP430s. You can see here the various numbers of these processors. I'm not going to read them. It is relatively small embedded software, but it's not tiny, tiny small, right? It's not like an 8-bit can do nothing kind of processor. It's reasonable, state-of-the-art today embedded kind of hardware stuff. They communicate through a UART connection, serial bus essentially, with MQTT, and then there's a bunch of network protocols talking to the outside world. And here is the software architecture. You have about 20 seconds to read all of that. But more seriously, the point of this slide is that all of these boxes you can see here are implemented in exactly this way as software components in the actual implementation. So that's not just a conceptual diagram. That's actually a representation of the software structure. The whole thing is without an RTOS, without a real-time operating system, and it's what's called a one-threaded programming model. So it's essentially a piece of code that is driven by interrupts, and the interrupts are essentially triggered at the sample rate that is necessary to do the precision computations we need to do. So I have a few screenshots of the extensions we've used so you can get an impression of how this stuff works. Stop, there's something else. I should say something about this. We did get from the processor vendor, we did get an example/reference implementation of a smart meter on this hardware. It was only on one processor, and it wasn't quite, the quality of the code wasn't quite the way we would have expected it, so we threw it all away. And as part of the implementation of Smart Meter with mbeddr, we had, therefore, 2 steps. The first one was essentially re-implementing the reference system, the example system with mbeddr from scratch, essentially retyping it and putting it, factoring it into components and using all the extensions we have. And then phase 2 was enhancing that with additional features that were required for our particular project by the customer. So we added, we split it onto 2 processors, added the communication between the 2 of them, added another communication protocols, implemented various communication messaging protocols and stuff. That's important later to look at the efforts because we separate that into the 2 phases. All right, the size of the system, you can count this in various ways, but I guess this is the interesting line. It's 15,000 lines of code that will later run on the device, and it's roughly another 15,000 for test code. So the system we've implemented is about 30,000 lines of code. That's not monstrous if you compare that to aviation or automotive software, but it's also not a toy, right? And here you can perhaps read, probably not, a few numbers regarding the kinds of stuff we had. For example, we have 300 functions. We have 140 software components in the system. We have 107 test cases with 2,500 assert statements. So you can see there is quite some test coverage, 80%. I'll get back to that later. And 16,000 statements, right? So I'm not going to read all these numbers, but this gives you a rough impression of the complexity of the system. We have 122 physical unit definitions, right? All various kinds of voltages and currents, and I don't even know the details. All right, so the code. Here is a little peek into mbeddr's components, right? You can define interfaces. You can then have components which implement these interfaces or require the interfaces. So you can do this typical component connection port kind of thing that you do in almost all embedded development methodologies. Here, of course, it's directly integrated with C code because mbeddr is a set of extensions to C. You can see a state machine abstraction here. To do state-based behavior. You can instantiate the state machine and use it. The state machine also has graphical and tabular notations you can use. This is a screenshot of the textual one because it didn't require as much space in the paper. Here is a test case that happens to test the state machine we've seen before, right? You can check whether something is in a given state. You can trigger an event. Here is a mock component we use for testing systems that are, component-based systems. Here you can specify the expected behavior and then use that mock in the test case, classical mock object kind of stuff. Here is an example of where we use mathematical notations plus units. So here you can see this function takes an int16 in volts and an int16 in amperes and calculates some average ampere. And then, of course, if you do a mistake with the units, you get an error, right? Here is product line variability stuff, a feature model, and essentially presence conditions annotated to the code. And now the things I've showed you so far are extensions that are kind of default available in mbeddr. This one and the next 2 have been developed specifically for Smart Meter. Here we have a way of directly representing registers of the processor, including the behavior that is done in hardware when you deploy to the real platform. This stuff is used when you simulate or test on the PC. So there's the kind of behavior reprogrammed that otherwise is done by the hardware, and you can access these registers as if they were global variables. We have interrupts as first-class citizens, so we can simulate the occurrence of interrupts in test cases on the PC when we test without hardware. And we have relatively sophisticated, well, not sophisticated, but a useful DSL for defining messages. I mean, you know how messages are defined usually with strange protocols in C. It's arrays and arrays and arrays where one array points to the other, and then you have the sum of the number of the fields in the other. It's total, I mean, it's really bad. And so having a nice language extensions that let you just declare these messages as if they were structs, even if the fields are not multiples of 8, is very useful. All right, that was the quick peek. Let's look at the answers to the research questions. Complexity. Well, it turns out that the developers we had on the team, that's an important constraint, naturally think in terms of some of the extensions. In particular, the project lead of this project, he did a PhD in component-oriented software for embedded stuff, and so he was quite naturally kind of inclined to think in terms of components and interfaces and polymorphism and stuff. That's not always true for all embedded developers, right? So, but in our case, it was true. The components help structure the system. Obviously, you know, breaking down big stuff into many smaller things helps. C isn't very good at that. The components help. And of course, we also, because we had interfaces partially with pre and post conditions, we could do strong static checking, which of course helped correctness and also readability. For example, when we had units in the code helped. State machines, as state machines are easier to read than state machines encoded as a switch case statement. Testing. We had a test coverage of about 80% of the core mission-critical components. Components meant literally components of the components. And generally, we had testability improved specifically because we could remove the component, take the same interface, plug in a mock object. That always helps. The custom extensions facilitated hardware-independent testing. We could essentially run the whole system before we even had the hardware. Of course, not for timing and resource consumption testing issues. That obviously needs the hardware. But the functionality was tested completely on the PC. And, the modularization also helps track down problems when you commission the system, because you can first start deploying only a part of the system, see if that works, and then you add components as you go, and then if something goes wrong, it was probably the component that you've added last. Overhead, again, we didn't compare it to a non-mbeddr implementation, but we were able to run the system on the hardware that was planned without knowing that it was to be built with mbeddr. So we could kind of run it on the, there wasn't too much overhead, so we couldn't run it on the intended hardware. I guess that's the way to say it. And the performance was good enough to achieve these 4096 hertz of sample rate. Right, that's what we can seriously say. We didn't, couldn't compare. Effort, here is the effort that we spent, and let me point you to these two numbers. They're most interesting. Only 13% was spent on integration and commissioning. That's rather low for embedded software. Typically, the integration and commissioning effort is higher. You can read numbers of up to 40, 50, 60%. So that was quite nice. And only 5% were spent on building new language extensions. 5% is something that most projects, I would say, are able to absorb. So, it's not a lot of penalty you pay to build new extensions if you think they're useful. 5% is not bad. I mean, also, we didn't build monstrously big extensions, right? These registers, messages, and stuff, they're not that complicated to build. So, I just said this. I just said that as well. And yeah, the overall effort of building the system was, I don't exactly remember the number. It was within a few percent of what was originally estimated. So the effort, there was an estimation of what the effort would be with mbeddr, and then there was the real thing, and it was roughly in the same ballpark. It was an experienced developer. He knows how to estimate, but the point is there were not a lot of bad surprises as a consequence of using this new tool. So a little bit of discussion, and I have to make sure I don't run out of time. In the paper, we discussed various aspects of validity. I'm not going to go through all of them in detail, but we discussed, for example, whether the team was biased, because, of course, me and some of the authors built mbeddr, so we obviously do have an interest in, selling it, in quote, as something that works, but we tried as much as possible by collecting actual data to de-bias this as far as possible. Also, Ari helped with that, because he didn't build this. Team expertise, of course, the mbeddr developers were available to the smart meter team to help if that was necessary. So these are all constraints you have to take into account. Conclusions, there is one interesting aspect that came up also during the review. Could this be done? Did these benefits come from tool or from language extensions? Right? Could you get the same language extensions benefits without the tool, or could you use a tool without the language extensions? I think you can't separate them. And we didn't test. We only had the tool plus the extensions, the IDE and the language extensions. And of course, we discussed how this can be used to other systems beyond smart meter. So discussion, the Debugging is something that is crucial. We were debugging on the level of the generated code and on the level of the extensions. mbeddr has a debugger to run debuggers on the extension level, but people also wanted to debug on the lower level to understand fine details. Code quality was good enough for, well, you can see here we kind of automatically fulfilled 25% of MISRA compliancy. The other 75% we need to look at. Maintainability, we don't have a lot of long-term experience with smart meter, we just build it, but we can say that this two-phase thing where we had phase 1, rebuild the old one, and then phase 2, add additional functionalities, almost a bit like maintenance, and that worked. So drawbacks and challenges, and then I'm almost done. We didn't do a lot of generator optimizations. It wasn't a big problem because essentially all extensions are still imperative, kind of, so it's not that complicated to map them to C code. If we had a different computational paradigm, the effort to build optimizing generators is higher, and it's probably quite a bit higher. You have 2.5 times longer build times because you have these generation steps down to C. That's something you have to deal with. Tool lock-in, there's no way to do that without mbeddr and MPS. Just no way. If you don't like that, you're out of luck. Diff merge works only in MPS, but it does work, so teamwork works as long as you use the tool. There's a learning curve, both to building languages with MPS and also to using mbeddr to build stuff. Yes, 2 minutes. And obviously, if you want to build new languages or new language extensions, you need language engineering skills. So, conclusions. We think that the extensions in mbeddr and those that we build help master complexity, make things more testable, and integrate and commission things more easily if you're willing to buy into the story, right? You have to go full in, use mbeddr for everything, and if you don't want to do this for the drawback reasons I just mentioned, then that doesn't work. The overhead is, well, I said very low. It's low enough to be practically useful. It's not free, even though we have a few extensions. For example, the units, they just type system extension, no runtime overhead at all. So depending on which extensions you use, you pay a little bit of a price, but not a lot. Effort is reduced, especially in the commissioning phase. That was really surprising to us. We didn't expect that. In terms of generically language extensions, based on the experience we've made here, we do consider language extension a fruitful approach. We use it in other domains as well, for example, in insurance systems, in engine management, and in robot control. Daimler is actually currently building a system based on this infrastructure for industrial robot control. In terms of case study research, we think that having case studies based on real industry projects is certainly a useful approach. I'm not saying other specifically set up case studies with students or something aren't useful, but I think maybe what I want to say is that doing more case studies on real industry projects is probably worthwhile doing. All right, I think I have 30 seconds left, so I'm earlier than planned. Questions?